Cool. Hi, everyone. I'm Adrian. I'm a postdoc at Princeton University and also here at the Flatiron Institute. Um, and I'm also part of the local organizing committee. So if you have any questions about the conference, please feel free to ask on the New York side. Also, I want to mention that I did a lot of this work during my PhD at UC Berkeley. How do I change the slide? Oh, great. Cool. Okay. Cool. Okay. So let me start by breaking down the title of my talk, Cosmological Field Level Inference with Microcanonical Langevin Monte Carlo. So let's start with the word cosmological. So a current problem in cosmology is we have these images of the universe, for example, a 2D weak lensing map or a 3D map of galaxies in the universe. And we want to try and infer the cosmological parameters, for example, S8, the Hubble constant, the dark energy parameter, primordial non-Gaussianity, or neutrino mass. And traditionally, the way this is done is using the two-point correlation function. So you look at 2 points in your map, you see how correlated they are as a function of the distance between them, and use this as a summary statistic to learn about the cosmological parameters. But as you probe smaller and smaller scales, like current surveys are doing, this no longer is optimal. This no longer gives you all the information. And so you have to move beyond the 2 point correlation function to get all the information. And one way to do this is using higher order statistics. For example, you could look at the halo mass function, which looks at the distribution of masses of halos in your map. Or you could look at the void size function, which looks at the distribution of the volume of voids in your map. And you can use each of these different summary statistics to infer the cosmological parameters. And we found in the context of neutrino mass that if you just look at the 2 point correlation function, which is the red contour in the plot on the right, you get constraints of 1 EV for the neutrino mass. But using all three statistics and combining them together, you can get orders of magnitude tighter constraints. So this is showing that there's a lot more information than just the 2 point correlation function in your map. But we just used some higher order statistics here. There's no guarantee that this will give us all of the information in the map. So the question we want to answer is, can we find all of the information in the cosmic fields? And that leads me on to field level inference. So the idea of field level inference is that you start in the early universe where we know that the density field is normally distributed. So if you look at any pixel in your map or any voxel in your 3D map, the density field will be normally distributed. And then you have some forward model, which takes your initial modes and the cosmological parameters lambda, for example, sigma 8 and omega m, and then gives you some final field, for example, the galaxy field or weak lensing field. And the idea of field level inference is to take this backwards. So to go from this final field that we observe back to the initial conditions, so infer the initial conditions of the universe, as well as the cosmological parameters. And you can do this with a likelihood, you can do this without a likelihood. I'm going to talk about the likelihood approach in this talk. And so mathematically speaking, what we have is some posterior, which is a function of the initial modes S, so that's every pixel in your map, and the cosmological parameters lambda, given some data D. And this consists of a likelihood term, which just tries to match the data D to the forward model F, and some noise associated with your measurements N. And then a prior term, which is just saying that the initial universe is normally distributed with variance given by the power spectrum. And then the sum is over all the pixels in your map. And this is a very challenging task because this S parameter is every single pixel in your map. And for upcoming surveys, we're going to need millions or even billions of pixels in order to do this analysis and extract all the information. And so in order to make this into a reality, there are three key ingredients that we need. We need a fast forward model in order to evaluate the posterior quickly. We need a differentiable forward model in order to get the gradient of the posterior quickly, which will be used for inference. And we also need a fast sampler. The first two of these problems we can fix by using PMWD, a differentiable code written in JAX. And this is able to fit 512 cube particles on a single GPU and can do one n-body steps in 0.1 seconds, which is extremely fast. And because it's written in JAX, it's auto-differentiable, which means you get the gradients of the forward model for free. And so that solves the first two problems. I should also mention there are other ways to do this. You could use the Borg approach, or you could use effective field theory. Both are also fast and differentiable. And so, yeah, so we've got a solution to these first two problems, but the final problem now is we need a fast sampler. And that leads me on to the next part of the title, Microcanonical Langevin Monte Carlo. So the traditional sampling method people use is Hamiltonian Monte Carlo or canonical Hamiltonian Monte Carlo. The problem setup is that you have some, say, 1D probability distribution, P of X, on the top left. And in Hamiltonian Monte Carlo, you introduce some new momentum parameter pi, such that the joint distribution of X and pi is proportional to e to the minus h, where h is the Hamiltonian. And then the Hamiltonian is derived such that when you marginalize the joint distribution over pi, you get P of X back. And then once you have your Hamiltonian, you can derive the equations of motion and follow these equations of motion to get samples of your parameters. And so what's happening in the bottom left over here is it follows the Hamiltonian trajectory. And then you notice that there's some jumps, because it turns out that if you followed the Hamiltonian dynamics exactly, you wouldn't get accurate samples. And so in Hamiltonian Monte Carlo, you have to resample the momentum, change energy levels from time to time, and pass and accept, reject Metropolis Hastings step. So the trajectory kind of follows constant energy for a bit, then takes a jump, then follows constant energy for a bit, then takes a jump to another energy level, and so on and so forth. And so this seems somewhat suboptimal. And that's what motivates microcanonical Hamiltonian Monte Carlo, which follows the same idea, but now instead of making the joint distribution proportional to e to the minus h, you make it proportional to the delta function of h minus e, where e is some constant energy. And now you can follow this constant energy surface in your pi x parameter space and get samples while conserving the energy. And this trajectory looks a lot cleaner. And mathematically speaking, what microcanonical Hamiltonian Monte Carlo is doing is adding this extra piece to the equations of motion. Here, z is the position and u is the velocity. So in standard Hamiltonian Monte Carlo, the velocity du is given by minus the grad of L. But in microcanonical Hamiltonian Monte Carlo, you have this extra piece, which depends on the dimensionality d, and also this projection operator of the velocities, which projects the gradient of L onto the hypersurface perpendicular to the velocity. And then in microcanonical Langevin Monte Carlo, we just add some extra piece, which is a stochastic term, this eta dw term. dw is just some normally distributed random variable and eta some tunable parameter. And adding this stochasticity helps improve the quality of the samples and the efficiency of the algorithm. And so now that we have our sampler, we can put everything together and do cosmological field level inference with microcanonical Langevin Monte Carlo. And so this is the experiments that we've been looking at. We've been looking at nonlinear dark matter, both 1 LPT, 2 LPT, and 5-step particle mesh, so different levels of nonlinearity. We've looked at 16 cube, 32 cube, 64 cube dimensionality. The voxel size in our problem is 4 megaparsec over h, so we're really probing the nonlinear scales. And we inject some noise. So the setup is on the right. The orange line is the true power spectrum of the data that we're considering. And then we add some noise given by the red line, which leaves the data, which is the green line. And just to visualize the problem, we have a final field on the top right, which is the data that we observe. We have the initial conditions on the top left, which is the true initial conditions, which gave rise to the final field. And we want to sample the initial field by matching the final field to our forward model. And so if I click this button a few times, you can see that the sampler starts to converge to the true final field, and we can start to sample the initial conditions of the universe. And so looking at this more mathematically, we want to look at how good the quality of our reconstruction of the initial modes is. And we can look at the cross correlation between the reconstructed initial field and the final field on the left. And you can see that the cross correlation between reconstructed and the true field is very good on large scales and starts to deteriorate on small scales because of the noise on the small scales. And then you also see the transfer function, which looks at the amplitude between the true and reconstructed field is very good and close to 1. And crucially, you can see we tried HMC and MCLMC on this problem, and both give identical samples. But MCLMC is 22 times faster than HMC. And I should say this is for a 32 cube problem with 2 cosmological parameters, omega m and sigma 8. So a total of 32,770 parameters. And so now let's look at the parameters, the cosmological parameters, omega m and sigma 8. Again, HMC and MCLMC give very similar looking contours, which is very promising. But now the MCLMC is 42 times faster. And so this is very exciting. And what's even more exciting is the dependence on the dimensionality. So this plot is showing the effective sample size of MCLMC compared to HMC. Effective sample size is a measurement of the efficiency of the algorithm. And you can see that as we go to higher and higher dimensions from 16 cubed to 32 cubed to 64 cubed, the effective sample size of MCLMC becomes larger and larger compared to HMC. And this is really exciting because if we want to apply this to real data, we're going to need to go to dimensionality of around 512 cubed to really extract all of the information. And so we're very optimistic that using this new sampling method will allow us to actually apply this to real data very soon. And then looking further forward, all these new surveys will be giving us information in various cosmological probes, for example, the CMB, Lyman alpha, weak lensing, and galaxy surveys. And we're now at a stage where we can start combining the information from these different probes to extract more information. For example, you could combine information from the galaxy density field with the peculiar velocity field to get more information about the growth rate or the neutrino mass. And I think moving forward, what we really want to do is combine all the information in all of these fields in some field level inference framework. So to have a forward model, which takes you all the way from the CMB down to very current times with large scale structure. And this is something I'm working on with people at the University of Tokyo, the half-dome simulations. These will be some very large simulations which simulate all the way from the CMB down to large scale structure. We're going to have our first paper out soon, which will publicly release 10 simulations, which isn't quite enough to do field level inference yet, but it should be enough to start doing some interesting science with cross correlations between the cosmic probes and eventually lead the way to do field level inference of the whole universe. And on that note, I'd like to thank you for your attention, and I welcome any questions.
Yes. Okay, so the way that it works is that we will take a question from here, then another question from Slack, if there is any, and then another question from Paris. So let's start here. Is there any question here? I have maybe one.
Sure.
So what is kind of the minimum scale that you can go? You can in principle go to completely non-linear scales, or are you know?
So yeah, it very much depends on what probe you're looking at. For example, I mean, in this examples I was showing, you're looking at dark matter, and there we could go as far as we like. But then as you move to the galaxy field, for example, you could use an effective field theory model, for example, to get to K of 0.5 in real space. But in redshift space, then it becomes more difficult, and you're looking at around K of 0.2. And so I guess, yes, maybe we need some better models using machine learning to really probe to the smaller scales when it comes to galaxy surveys.
Okay. Do we have any question from Slack?
This is asking, are divergences as powerful a diagnostic for MCLMC?
Divergences. What is meant by divergences?
Ask him to elaborate, but
yeah, I don't know what you mean by
divergences. Can you elaborate more?
We can come back to this.
Okay. In the meantime, is there any question from Paris?
There's one from Torsten.
Please.
Hi, this is very nice. Can you explain the trick why your microcanonical sampler produces the right statistics when it changes energy levels?
Without changing energy levels, I guess you mean. So the main reason why it's so much more efficient is that in HMC with this Metropolis Hastings step, you have to make sure that the error in your energy is very small. Otherwise, you'll always fail the accept reject Metropolis Hastings step. But in MCLMC, there's no Metropolis Hastings step. So if you just have a slight deviation in the energy, even a small energy error, you'll still go through and get accurate samples with a much larger step size. I'm not sure if that answered your,
So you are not changing the energy. I thought you are changing the energy with your Langevin term.
Oh, no. So if I go back to that slide, so you mean the stochastic term, why does that work? Why does, I misunderstood your question, sorry. But yeah, in the Langevin part, the randomness that we're adding is actually still conserving the energy. It's adding some stochasticity such that the energy is still conserved. And so the samples are still accurate. So if you look at this term here, the projection operator of MCHMC is acting on the sum of grad L and the stochastic term. So because the stochastic term is in this bracket, the energy is still conserved. And so you still get accurate samples.
Okay, thank you.
Okay. Do we have more from Slack?
Johannes is still elaborating, but we have another question from Fleur saying, can you use this technique for higher point functions?
You mean like endpoint functions? Well, I guess the point of field level inference is to do away with the endpoint correlation functions. But in principle, yes, one could look at the endpoint correlation functions like any other high order statistic and get constraints that way too.
And Johannes's follow-up is, in HMC, you can check that the model is sampled correctly by observing gradient divergences. So can you do the same thing with MCLMC?
I suppose so. Yes, it's not something we've looked at, but yeah, I mean, looking at the gradient and how stable it is something we use in fine tuning the parameters to actually get the right parameters for the sampler. And so, in a sense, we're using that to tune the parameters. And I guess looking at what that's like when we actually do the sampling would be an interesting diagnostic.
Okay, I'm gonna take a question from Sultan.
I'm just curious if you tried applying this to data.
Yeah, not yet, but definitely that's the next thing on the list.
Yeah,
Not,
we should probably
sick.
go on.
Did you have a follow-up question?
No, let's go on to the next talk, Paco.
Okay, sounds good. Thank you.
Okay, thank you,
Thank you for the
Adrian.
talk.
Okay. So now we have Daniel Angles Alcázar, who's going to talk about camels.